This is the Level 2 2016 Waves exam. For this question, for this video, I'll be working through question 3. Question 3: washing the car. Anna is washing her car and notices that she can see drops of water on the windscreen, even though both the glass and the water drops are transparent. Why is Anna able to distinguish, I believe it's Anna or Anna, whatever, able to distinguish between the glass and the water? So they had different refractive indexes, different refractive indexes. I need to spell that correctly. Or optical densities. No, I don't really like the word optical densities because it's weird, but they had different refractive indexes. That's the proper way, i.e. Water has an N equal to 1.33, whereas glass has an N of 1.52, I think. There we go. And there's a neat wee experiment you can do with this. If you get, I believe it's castor oil, I think so, or it might be castor oil or olive oil, and you put borosilicate glass, so test tube glass or beaker, and you crush it all up and put it in a beaker. They're both the same refractive index, so your glass inside the castor oil becomes very hard to see because they're both exactly the same refractive index. Anyway, Anna tries to sketch a drawing of a large bead of water on a windscreen to help her understand what's happening. Use the information below to answer part B. If the air to water interface and the water to glass interface are roughly parallel, that's these lines here, calculate the angle of refraction in the glass. So this one way down here as labeled. So this is sort of a two-step problem. You're going to have, this is 32 degrees, we'll just quickly label that. This is going to be the second angle, so we'll call this theta 2, and then we'll call this here, I might move it to the side, theta 3, even though it's this theta is this angle from the ray to the normal. So it's always from the ray to the normal, it's never from the ray to the boundary. And normal is a synonym for, you know, at right angles, or tangent, or can't think of any other synonyms for normal. Perpendicular, it's a synonym for normal. Right, so let's start it off. So initially we go from air to water. So air to water, we're going to have to use Snell's law. So if we jump onto our formula sheet, where's Snell's law? Here it is. N1 sine theta 1 equals N2 sine theta 2. So we're going to have N1 sine theta 1 is equal to N2 sine theta 2. We have N1 is air, so that's just going to be 1. So this is N1. Water we'll call N2. Let's label it up there. And theta 1 is 32 degrees. So we're trying to find theta 2. So theta 1 is 32 degrees. So what we're going to need to do is we'll divide both sides by N2. So divide by N2, cancel that out, divide by N2. And now to get rid of the sine, we need to take the sine inverse. So basically it means we need to go sine inverse of this whole side. So we'll just put brackets all the way around it. N1 over N2 sine, I'll just put the degrees in, 32 degrees, yep. And then if N1 is 1 and N2 is 1.33, plug that into your calculator, you will get 20, I'll just put it down here, theta 2 equals 23.48 degrees. We'll leave it to an arbitrary amount of significant figures for the moment. Right, so that's theta 2 is now 23.48, yep. Now we need to find theta 2, so we theta 3, water to glass. Same thing again, we don't really need to rearrange, we can just use this formula that we had up here. In other words, theta 3 is equal to sine inverse N2 over N3, because originally it was N1 over N2, now it's going to be N2 over N3, sine, but now we need to use this angle here, 23.48. 23.48, bracket around that. If you plug that into your calculator, N2 being 1.33, N3 being 1.51, because this is, here we got N1, here we got N2, here we got N3. So these are the different optical densities of the various things. So if we plug that into your calculator, N2 being 1.33, N3 being 1.52, it gives us 20 degrees. So in other words, our angle of refraction OR is 20 degrees. Right, state two conditions necessary for total internal reflection to occur. So condition 1 is the obvious one, the angle of incidence, so the angle coming in, incidence, let's spell that correctly, must be greater than not that, the critical angle. And if this isn't familiar to you, just look it up. Just look up critical angle of anything really. Look up total internal reflection. That's probably the better thing to look up. Second one, light must travel from a higher refractive index, refractive or optical density, but I prefer refractive index to lower, e.g. N1 to, I know what, I need to put the actual numbers in. N1 equal to 1.5 to N2 equal to 1.33. So glass to water. In other words, you need to go from slow to fast, because when you go from a slow to a fast, so water travels, light travels slower in glass than it does in water. When it hits the boundary, the speeding up causes it, if we go back to the previous question, causes it to refract and bend away from the normal if it goes from slow to fast. So we need to go backwards if we're going slow to fast. It bends away from the normal, and if you bend too far away from the normal, you'll eventually get to 90 degrees, and after you get past 90 degrees, total internal reflection will occur. Right, last question. Complete the diagram below to show the path of the laser beam in the stream of water. On your diagram, mark the angle of incidence. The normal has been drawn for you. So I am going to need my trusty ruler. I'm going to put it in line with this laser beam, and it should meet on that wee dot there. It should, fingers crossed. Yep. So that's where it gets to. Now this is just law of reflection. Snell, or I don't know, is it Newton's law of reflection or Snell's? I always forget whose. In other words, this angle here, theta 1, is going to be equal to theta 2. So theta 1 is equal to theta 2, and that's just the law of reflection. Yep. If the critical angle for red light is 48.70 degrees, calculate the refractive index of water for red light to 3 decimal places. So for starters, we're going to say water to air. There's a fairly big assumption that we're making here, and that is that this out here is air. For all I know, this could, it doesn't say it's air, but we're just assuming that. So assumption, I'll just write this, assumption, because nothing that says it's not air. That's what this is what I'm assuming, water to air. That's my assumption. So this is water and that is air. In other words, this is N equals 1 point, we're trying to work that out, aren't we? Trying to work that out. N equals question mark, N1 equals just 1, because it's air. Our incident angle is 48 points, so our theta 1, and forget about this stuff up here, I'll put this down here actually. Theta 1 is equal to, as I say, 48.870, and our theta 2, because it's the critical angle, it's going to equal 90 degrees. So N1 sine, move that up a bit, theta 1 equal to N2 sine theta 2. What we're I'm missing an N. Trying to find is N2. We've got everything else. In other words, N1 sine theta 1 divided by sine 90 degrees, because theta 2 is 90 degrees, equals 1. If you do that in a calculator, equals 1 divided by 1. So we're going to equals, and if you just plug this into your calculator, you're going to have, hold on, I've done something wrong. No, I've done this backwards. Take this back. N1 is water, because it starts in water. This is N1 and this is N2. Because this is where it starts. It has to go from slow to fast. So in other words, this here, I'll just quickly cross this out. This is the water, this is the air. This is still 90 degrees, that's still 48, and this is 1. So in other words, and sine 90 degrees still equals 1. So nothing's really changed. This is still 1. So I'm going to go N1 equals N2 sine theta 2 divided by sine theta 1. We can't see that. And now N2 is 1, sine theta 2 is 1, so it equals 1 divided by sine theta 1 is 48.7, 48.7, and that gives me an answer of N1 is equal to 1.331. So that's 3 decimal places, not 3 significant figures. And that's it.